Good evening, everyone. In today's video, we are going to perform a ball impact analysis in Abaqus, and more specifically, we are going to understand the difference between low velocity impact and high velocity impact. We'll look at something very important in the impact simulation, that is the contact definition. Because when a ball hits a structure, we are dealing with highly non-linear behavior because we get to see large deformation, material non-linearity, the changing contact definition, high acceleration, possible separation and recontact, and potentially very short simulation times. So simply applying a force to the plate is really not the representative of the physical problem. Instead, we want Abaqus to actually calculate the interaction between the ball and the target. In this example, we will use a spherical ball impacting a deformable plate. We will look at low velocity impact first, or LVI, and then increase the impact velocity and observe how the physics changes. By the end of this tutorial, you should understand how to set up a model, define the contact, assign appropriate boundary condition, use RBD physics where appropriate, and interpret the impact result. So what actually is low velocity impact? Let's understand that. What we actually mean by low velocity is low velocity impact, commonly known as LVI, which refers to an impact where the velocity is relatively low and the response of the structure is generally dominated by the structural deformation and its contact interaction. A typical example could be a ball hitting a panel, a tool dropping onto a component, or a low speed collision between two objects. Another practical example is low speed vehicle collision. For example, consider two vehicles in a parking area. If one vehicle moves into another at relatively low speed, the resulting event can still generate deformation and damage. The important point is that the term low velocity does not simply mean that the velocity is numerically small. That's a general misconception that a user has. The physical response depends on several factors, which are mass, velocity, geometry, material properties, structural stiffness, contact characteristics, and the duration of the impact. As we know, the kinetic energy of the impacting object is particularly important. So if we double the velocity, the kinetic energy increases by the factor of 4. As we know that k is equal to half mv square. This is one of the reasons why increasing the velocity, impact velocity, can dramatically change the response. Now let's compare low velocity and high velocity impact. In a low velocity impact, the structural response often has enough time to propagate through the structure during the impact event. We may significant deformation, or we can say that is global deformation, bending, local indentation, contact pressure, and elastic or plastic deformation. High velocity impact is a different problem. It's a different altogether scenario. The event occurs extremely quickly, stress waves become extremely important, and the response can become highly localized. Depending on the velocity and material involved, we may observe severe plastic deformation, fragmentation, penetration, material failure, erosion, and shockwave effects. Typical high velocity applications include projectile impact, ballistic impact, bird strike, high speed debris impact, and protective armor studies. So although both are technically impact problems, but underlying physics can be significantly different. And in today's problem, we'll keep the same basic ball and plate model and change the impact velocity to demonstrate how to see a response get evolved, or how the response evolves overall. Now the question arises is, why are we using explicit analysis or Abaqus explicit? Because impact problems are highly nonlinear and often involve severe contact and large deformation. Abaqus explicit is particularly well suited for these transient dynamic problems. Unlike a implicit solution procedure, where the explicit method advances the solution using very small time increments. This makes it extremely effective for problems involving complex contact, large deformation, rapid loading, material failure, and severe nonlinearities. The major downside that it carries is that the stable time increment can become very small. So computational efficiency at your end or upon the hardware becomes very important. This is where modeling choices comes into the picture. That is the mesh size, element type, material density, mass scaling, and rigid body, which is very, very important. Now I told you that impact problems are highly nonlinear and it often involves severe contact and large deformation. So both are technically impact problems, that is the low velocity and high velocity. The underlying physics can be significantly different, as I told you. Because in high velocity impact, we calculate severe plastic deformation. We get to see fragmentation, penetration, material failure at very high speeds, erosion and shockwave effects. Generally visible in seismic loading conditions as well. So as we know that Poisson's ratio is the ratio of lateral strain to longitudinal strain where a material is stretched or compressed. We have elastic moduli as well, according to the Hooke's law. So after performing a static or a basic static analysis, we can advance upon the low velocity analysis or the high velocity impact analysis. Because we are using an explicit analysis solver or explicit analysis, it becomes very effective for studying complex contact, large deformation, rapid loading, material failure and severe nonlinearities with the inclusion of dynamic problems as well. And I told you that modeling choices can very much compensate upon the speed of the analysis. That is mesh size, element type, material density, mass scaling and RBD. Now look at our model. We have three primary components. First, we have a ball which will act as the impactor. Second, we have the target plate which will deform during the impact. And third, we have the surrounding reference geometry and boundary condition required to represent the physical setup. So for the ball, we have two possibilities, that we can model the ball as a deformable body or we can model it as an analytical rigid body which is not deformable. If deformation of the ball is not important, using a rigid body can significantly reduce computational cost because we don't consider deformation in a rigid body. So this is an important concept. A rigid body does not require a conventional deformable body mesh for its structural deformation. Instead, its motion can be controlled through a reference point or RP. The rigid body can translate, rotate about its reference point. This is where RBD concepts become very useful. There is an important distinction that a rigid body can participate fully in the dynamic contact problem. It doesn't necessarily mean that the entire simulation becomes a rigid body only simulation. For example, our ball can be rigid while the plate remains deformable. The ball transfers momentum and energy to the plate through contact, and that's when the rigid body dynamics come into the picture. Although it's not a dynamic analysis and we are not considering any external force on that whole surroundings of the ball and the plate, but we need to consider some component, that is plate or the ball, as deformable, because that is when only we can calculate the impact analysis or we can see a ball, plate gets deformed. Now when I start with the part module, for the plate we can create a 3D deformable solid. For example, we can use a rectangular plate with the appropriate thickness. The exact dimensions are not necessary and are not important for understanding the workflow, but they need to represent the real component as we are studying them. So I'll include Young's modulus, shear modulus, bulk modulus and Poisson's ratio. Young's modulus has it known as elastic modulus. Bulk modulus, that is the volumetric stress upon volumetric strain, and we know about the Poisson's ratio. The negative sign in the Poisson's ratio is used to show that the deformation is in the opposite direction to the longitudinal. We can obviously include thermal strain or we can include the volumetric strain. Thermal strain occurs due to the change in the temperature. We can include that in this particular analysis. We know about the yield point. Material starts to deform plastically at the yield point and stress remains constant or slightly drops while the strain increases. That is known as the yield point. So for the ball, we can create a sphere. If we are treating it as rigid, we can create an analytical rigid surface. This is useful when the ball's deformation is negligible compared to the deformation of the plate. Now let's create the material for the plate. At the minimum, we need density, elastic property, and if we needed, the plastic deformation is expected. Plastic material data is also required. For a basic elastic material, we need to define Young's modulus, as I told you, and Poisson's ratio for the basic requirement. But for impact analysis, don't forget density. Density is not optional in dynamic impact problem. Abaqus needs to calculate the inertia and kinetic energy. If plastic deformation is expected, we should also define the appropriate plastic stress strain behavior. For high velocity impact, material modeling can become much more sophisticated. So we need strain rate dependence, damage initiation, damage evolution, and failure, and potentially a equation to govern all the state of extreme impact regimes. So the material model should always be selected based on the physical problem. Now we are defining the strain rate dependence. This helps us also include that the angular deformation between two originally perpendicular lines gets the formula of volumetric strain, that is delta V by volume. Delta V, that is the change in the volume, and V is the original volume. Material we are considering isotropic, because we know the difference between isotropic and anisotropic. The major one is in the behavior. Isotropic behaves same in all the directions, and isotropic varies in the different directions. Isotropic, I can give you example, that is steel and aluminium, and anisotropic, that is composites. Isotropic is very easy to model, and it's a single step of property. But in anisotropic, that is also the capabilities of Abaqus. We can also define anisotropic materials. We need to define the direction specific to material data. So what is the main application of stress transformation in simulation is understanding local stress on inclined plane, finding principal stress in planes, finding maximum shear stress, that is the equal of radius of Mohr circle, validation and verification, and design discussion, that is modify material geometry where stress concentration appears on the critical inclined plane or the critical planes. Now let me give you a brief about stress transformation equations that is used to define the normal and shear stress on a plane inclined at the angle theta related to the original coordinate axis. We know sigma x equal to normal stress in x direction, sigma y, that is normal stress in y, tau xy, that is shear stress, theta, that is the angle of plane between x-axis, and we know that there are multiple equations for governing the normal stress. Now let's move to the assembly module. We initiate with the plate, then we mate the ball. For a rigid ball, we create a reference point, that is the RP, which will control the rigid body's motion. We then associate the rigid spherical surface with the reference point using the rigid body definition. Conceptually speaking, you can think of this reference point as the point through which we can control the rigid body. We can prescribe initial velocity, translation, rotation, or any other appropriate motion quantities for governing this ball's motion. For this impact problem, the important quantity is the initial velocity of the ball. Contact is equal to the heart of impact simulation. I hope you get what I just said. The contact is the most important part of the entire simulation that we are setting up. When the ball approaches the plate, there is initially no physical interaction. Then the ball touches the plate, contact is established, the plate starts deforming, the ball may then slow down, stop, and potentially rebound. That is very critical, that it should rebound, because that is the original physical behavior we expect from a ball when it touches the plate. So the contact state is continuously changing during the simulation. In this explicit solver of Abaqus, we can define general contact for complex contact interaction. For a simple ball and plate problem, we can define the interaction between the ball surface and the plate surface. There are two fundamental concepts we need to understand, that is the normal behavior and the tangential behavior. For tangential behavior, we are going to discuss that for the normal behavior, we generally want the surface to resist penetration. A commonly used approach is hard contact in the normal direction. This means the surface can transmit compressive contact forces but should not physically pass through each other. Next one is very critical, that is the tangential behavior. This is where the friction becomes very important, and we need to define a friction coefficient. Let me just find out. So if a ball is intended to bounce almost vertically without significant sliding friction, this may have a relatively small influence of friction. But if the ball strikes the plate at an angle, or if rotational motion is involved, friction can become much more important. For example, imagine a ball hitting a plate at an angle. Now the contact forces has both normal and tangential component. Now just note down that friction can influence ball rotation, sliding, energy dissipation, rebound direction, and local stresses, as I told you. Therefore, contact properties should be set up based on experimental data whenever possible and not on your intuition. Now, let's set up the boundary condition. We are fixing up some edges as I highlighted these. Next, we need to define our boundary condition. The plate cannot simply float freely in our physical test that has the plate clamped. So we need to represent the actual experimental setup. But be careful, over constraining the model can produce unrealistic stiffness. Under constraining the model can cause unwanted rigid body motion. The boundary condition should represent the physical fixture. Now for the ball, we need to necessarily need to prescribe a force. Instead, we can give the ball an initial velocity. This is much closer to the physics of the impact event in real life. For example, if the ball is moving vertically downward, we need to assign its initial velocity in the negative direction, or we can just simply define the gravity of the ball when we are giving it direction of vertically downward. Now let's run this analysis. After it gets completed, notice what happens. The ball approaches the plate, contact is established, the plate begins to deform, the ball loses velocity, and then depending on the material boundary condition, the ball may rebound. So the most important takeaway in this simulation study is that impact simulation is not simply about applying a large force in the numeric input values. It's about correctly representing mass, velocity, momentum, contact, material behavior, deformation, and large transfer of energy. And when those physics are modeled correctly, Abaqus Explicit becomes a very powerful tool for understanding real impact problems. If you found this useful, make sure to follow. Thank you so much.